Excellent. Well, welcome everyone. My name is John Bilotta, and I'm pleased to welcome you all to our 2023 Minnesota Stormwater Seminar Series. We are so pleased that you're joining us, and we are pleased that we're going to continue the seminar series through the calendar year. For 2023, our seminar series will consist of three distinct elements month to month. First, we will continue to feature nationally recognized experts on stormwater runoff and green infrastructure to share their wisdom and their knowledge and insights to help us continue to push the boundary of clean water management here in Minnesota, across the region, and nationally. On other months, we will feature our Minnesota research spotlights. During these seminars, we will feature some of the results of our research projects funded by the Minnesota Stormwater Research Council. And our third element is seminars on specific stormwater management practices and approaches, as is the featured element of today's seminar. This effort is brought to you by the St. Anthony Falls Laboratory, the Water Resources Center, and the Minnesota Pollution Control Agency. Our thanks to our financial supporters in this endeavor on the seminar series, the Minnesota Clean Water Land and Legacy Amendment, and the Minnesota Stormwater Research Council and its contributing partners. Before we introduce this month's topic and speakers, I'd like to take a moment to tell you about the calendar for the year ahead and some resources. Generally, the seminar series will be the third Thursday of the month, but not always. So please continually check the website for updates. Also, for February and March, we are going to return to an in-person opportunity as well as virtual Zoom seminars. So we will invite all of you from Minnesota that are willing and able to join us in person at the auditorium at St. Anthony Falls Laboratory. And as well as always, you can join us via Zoom. So you can see the calendar ahead here for the next 6 months. So please take note of these dates. I would highlight our July 20th date, which will be our annual Minnesota Stormwater Research Council meeting. As always, please visit the website for updates on these dates, the topics, the presenters, and the registration links. Finally, a bit about logistics before we begin today's seminar. We will use the Q&A feature of Zoom to ask your questions to the presenters. You may also give a thumbs up or a thumbs down to a question asked by one of your colleagues, and we will tackle as many of those most desired questions at the end of our presentations today. We are also including two new features for the seminar series here in 2023. We're going to request feedback from all of you using a short online form that will be inserted in the chat during the seminar. And also, if you desire professional development hours, we will put a request form in the chat as well, and you can fill that out to receive a PDH certificate. We will also put all these links in the chat, including the website, and just a final reminder that all of our seminars are recorded and available on the SAFL YouTube channel. Now on to today's seminar. This month's seminar focuses on stormwater infiltration. Stormwater infiltration, when appropriate, is a preferred stormwater management approach that provides communities, industries, and professionals opportunities to reduce runoff volumes, reduce pollutants, and in cases, help us enhance shallow groundwater recharge. Today's seminar will present some of the challenges in infiltration as a practice, discuss ways to address some of those challenges, and highlight some of the current research and resources available to practitioners and professionals. I would like to introduce our seminar lead and our colleague this morning, Mike Trojan. Mike is a hydrologist with the Minnesota Pollution Control Agency, and I suspect for many of you, he needs little to no introduction. Mike leads many aspects of stormwater management and practice development and implementation in Minnesota, and he serves as a lead on the Minnesota Stormwater Manual. Welcome, Mike, and please take our seminar away.
Thanks, John, and good morning, everyone. John gave a tremendous introduction to the topic, and so I'll just jump right into our speakers. I'm very excited to have them here today. Our first speaker will be Dr. John Gulliver. Dr. Gulliver is a professor emeritus in the Department of Civil, Environmental, and Geoengineering and a resident fellow at the Institute on the Environment. He received a BS from UC California, Santa Barbara, and MS and PhD in degrees in civil engineering from the University of Minnesota. Dr. Gulliver has taught courses in fluid mechanics, environmental mass transport, and hydrology and water quality. He's been faculty member for 40 years. Much of Dr. Gulliver's research in conjunction with other faculty involves the development of new technology, including the SAFL baffle, iron enhanced sand filter, and the MPD Infiltrometer, which I'm guessing he'll touch on today. He is co-author of the book, Optimizing Stormwater Treatment Practices, a Handbook of Assessment and Maintenance, published by Springer. Dr. Gulliver, welcome.
Thank you, Mike. I assume everyone can hear me.
Sounds good, John.
I tried to get Mike to give a very short introduction, but he didn't. So my topic today will be the importance of and methods for field determination of infiltration practices and infiltration rates. I am John Gulliver. This research was supported, we've done research for about 20 years. It was supported by the Minnesota Supercomputing Institute, the MnDOT through the LRRB, and lately from the city of Minneapolis. Okay, so I have many collaborators in this, so I'd like to go over this very briefly. My main collaborator for all these years, that's about 20 years of doing work, is John Nieber. We've been together on many infiltration research projects. I've also had co-PIs with Andy Erickson and Pete Weiss, and a number of students. Brooke Asleson was an early student. She is currently at the Minnesota Pollution Control Agency. Rebecca Nestingen, another early student, is currently at SEH, a consulting firm in town. Nick Olson is the head hydraulic engineer currently for MnDOT. Farzana Ahmed is currently in New Jersey. Nick Teka is in Michigan, and Maria Garcia Serrana is in California. So the agenda. We're going to start off with some background on infiltration practices. Why are we measuring infiltration rates? Why do we do this? How do we measure infiltration rates? And how many infiltration measurements do we need to take? One infiltration measurement is not sufficient. I'll explain that. Finally, is there bias in infiltrometers? Can you trust your infiltrometer to actually measure infiltration rates and measure your saturated hydraulic conductivity? And we'll finish with some take-home messages. So background on infiltration practices. This is a often used photo simulation by Chris May from the University of Washington. It depicts some forested land cover on the left and some urbanized land cover on the right. If you have a certain amount of precipitation in forested land cover, only 0.3% of that precipitation ends up as surface runoff. Now, these are simulations that he did probably with SWIM. In urbanized land cover, you have 30% roughly impervious surface. And all that impervious surface goes straight to runoff. So you have 30% surface runoff with an impervious land cover and with an urbanized land cover. That's a factor of 100 difference from a forested land cover to an urbanized land cover. That's the source of our problems in managing these types of things. So what can infiltration do for us? Well, the first thing it can do is reduce combined sewer overflows. It's not a big problem in Minnesota, but it is a big problem in many cities in the United States, especially towards the East Coast. A big problem in Minnesota, because we have so many lakes, is we also have pollutant loads to these lakes. Lakes sitting there, it has pollutant load coming in. We need to take care of that pollutant load going to our lakes and our rivers. It reduces the pollutant load because it reduces the water and the concentration that comes with it. A third impact is you can reduce the impact of extreme precipitation events. I did a research study with Tricia Moore and found that increasing infiltration practices reduce climate change adaptation costs by 50%. The reason for that is you can put in a lot of surface infiltration practices instead of going underground, which is very expensive. If you're going to have pipe upsizing or underground storage chambers, that costs a lot of money. You can do a lot of surface infiltration instead. But there are caveats to building infiltration practices. The main caveat is roughly 30% of infiltration practices fail on day one. That's kind of the history of infiltration practices. The reason is a lack of infiltration measurements. People put something in and assume that it's going to infiltrate. There is construction compaction, which can stop infiltration, basically stop it, and plants that don't grow. The plants open up the pores. Construction practices, construction compaction closes the pores. It makes a heck of a difference. So the question is, can you use soil texture tables to decide, if you take a borehole and see what's down there, if you decide, can you use soil texture tables to decide whether or not you can infiltrate water? The problem with soil texture tables is they don't talk about soil structure. Soil structure is what the plants do. The plants open up the pores. Soil structure is what happens with compaction. The compaction closes the pores. It makes a heck of a difference, and you really need measurements of infiltration. So how do you determine infiltration? Well, the most important soil parameter for infiltration rates is saturated hydraulic conductivity. We have a graph here on the right, infiltration rate versus time. The time could be minutes if you have sand or sandy loam, or hours if you have clay. You start with a high infiltration rate at time 0, but it goes fairly quickly down to something that's close to your saturated hydraulic conductivity. So it does set a minimum for your infiltration rate. I'm going to talk about 3 measurement techniques. We've been working on these measurement techniques for 20 years. We've recently been comparing them in a project for the city of Minneapolis. The first is water level measurements after precipitation events. It sounds like a natural. It rains, you see how it fills up, and you see how fast the water disappears. Pretty simple, except it ends up being complicated in practice. I'll show you that. The second is synthetic runoff testing. I like synthetic runoff testing. You do it under dry conditions, controlled conditions. You watch the water drain. The third is point infiltration measurements with infiltrometers. I'll talk about that as well. So the city of Minneapolis, we're doing water level measurements after precipitation events. We're actually comparing these 3 techniques. It costs about $5,000 per site, so you need a fairly large site to do this. The reason it costs $5,000 is you have high equipment costs. You have to leave the equipment in there. You have to know what the rainfall is. You have to leave the equipment on the site to get enough data so that you can analyze it. The equipment doesn't always work. Sometimes something goes out, misconnection of something, some sort of meter. So you have continuity issues because you don't have a full set of data. And also it's a difficult analysis. If you look at the graph on the right, we have flow rate, which is actually infiltration rate on the y-axis, and precipitation on the other y-axis. Basically, we have the bars at the top are precipitation, and the blue signal at the bottom is infiltration rate. Precipitation doesn't happen all at once. You have a little precipitation, then you have a lot of precipitation, even in Minnesota summers. And then you have a little bit of precipitation, maybe a lot later on. And so you get this kind of signal, which is difficult to analyze. And much of the money is spent trying to figure out what happened. So it may be okay for general assessment at $5,000 a site. It's actually more expensive than the other techniques. I love synthetic runoff tests. That's number 2. What you do is you use a water truck or a fire hydrant during dry periods. It doesn't cost that much to get a water truck out there. And it doesn't cost that much to use a fire hydrant. You place water level sensors in the basin. It costs roughly $3,000 per site. You feel the infiltration practice, like here on this these pictures, and then you watch it drain. You see how fast it drains. Here's a synthetic runoff test at a rain garden that we did early on, 2005, I believe. We filled this rain garden and then watched it drain. Here's what the data looks like. It's clean data. You have the ground level right here. That's the orange dotted line, and this is the water level. It comes down. It's pretty clean, repeatable, as a matter of fact. So if you want to know the saturated hydraulic conductivity, you can use this equation. It's mostly based upon the left-hand side of this equation here, your original depth and your drainage time, but then the soil moisture and the soil suction comes into it right here. It has a certain impact. The problem with synthetic runoff tests is that if you have too large of a practice, if you have, let's say, 10,000 square feet rain garden or a long swale, if you can't get enough water to fill that up. It's difficult to find enough water. For example, the city will not let you run your fire hydrant for an hour because that is a problem for any fires that occur. Water trucks do not have that much water in them. And so at that point, you need to do point infiltration rate measurements. Here's a fairly long, wide swale. They were measuring, taking 18-point measurements at one time. That's on the left. On the right is a rain garden at the University of Minnesota Duluth, where we're also taking 18-point measurements at once. Why do we take 18-point measurements of infiltration rate? Well, that's the question. How many infiltration rate measurements do you need to take? There is a great variability in saturated hydraulic conductivity spatially at these practices. These are a number of studies that have been done on various practices. And at the bottom here, that'd be the x-axis. Look at the numbers on the x-axis. We have 6 orders of magnitude there. That is a million. A factor of 1 million. So that means that if you're at the bottom and you have a measurement at the bottom and you go to the top and you have a measurement at the top, there's a factor of 1 million between the bottom and the top. And look at all the studies. We have many studies that almost cover that whole range, at least 5 orders of magnitude. There are some that cover 2 to 2.5 orders of magnitude, which is still a lot. And so that means that you need to take more than one measurement. If you take a measurement at one location and it happens to have the low infiltration rate, you're going to assume that you have no infiltration. If you take a measurement at the location with a high infiltration rate, you're going to assume you have high infiltration. The truth is somewhere in between. So we've been doing this for a while, and everything seems to come out in this graph here. We have developed a rule of thumb, and that is it takes 20 measurements to have the mean value of the measurements be within a factor of 2 of the true mean. 20 measurements to get within a factor of 2 of your actual infiltration rate for the practice. And that's a 95% confidence interval. That means 19 out of 20 times you will be within that factor of 2 with 20 measurements. Costs about $3,000 a site, about the same as a synthetic runoff test. And with 10 measurements, you're within a factor of 3. With 5 measurements, you're within a factor of 6. Is that a problem? Well, it is if you have a fairly large practice. But if you have a little rain garden or something like that, a factor of 6 is, I think, just fine if it's a little rain garden in your front yard. So on the y-axis here, we have the normalized mean value. On the x-axis, we have the number of measurements. We've taken a lot of measurements at some places to determine this graph and at various locations, and it always ends up being about the same. The 95% confidence interval will be the distance between the bottom and the top graph, and the mean is right in the middle at value of 1. So you have 20 infiltration measurements. How do you relate these measurements to drainage time? Well, you use the green amped assumptions, which work pretty well. You relate the 20 infiltration measurements to one bulk saturated hydraulic conductivity. So your bulk saturated hydraulic conductivity for the entire practice is determined by this equation here under number 2. And then for a flat infiltration basin, you apply this equation to determine your drainage time. Let's say you want to know drainage time. You can apply that where Ks is your bulk Ks. So we've addressed a number of measurements. We found that it takes a lot more than we thought it would. And that's why John and myself and Brooke Aselson and Rebecca Nesting developed the MPD, because we knew we had to take lots of measurements. And, you know, the double ring infiltrometer is a pain to use anyway. So you need approximately 10 to 20 infiltration measurements to characterize an infiltration practice. The question is, how accurate are these things? How accurate are these infiltrometers? So item 3B, is there bias in infiltration measurements? Again, the variability in the field. You cannot go in the field and determine the bias in infiltration measurements. We've thought about it, we've tried, it doesn't work. So we did a numerical experiment on the computer. We take a soil identified with a certain hydraulic conductivity, certain soil parameters, a certain moisture, and put it into the computer. So we take a soil, put it in the computer, supply our infiltrometer as it's used in the field, run the tests, and see how the measurement compares to the actual. So we have a measurement of infiltration rate with the infiltrometer, and we know the actual infiltration rate or the actual saturated hydraulic conductivity in the soil. We did this on 6 infiltration measurement methods, 7 soil types, and at 5 antecedent soil moistures. So here are the 6. A TurfTech infiltrometer is used at golf courses to see if they have to water. The modified Philip Dunn infiltrometer is something that we have worked on. The Satiro is a new infiltrometer developed by the Meter Group in California. The double ring infiltrometer is the standard. Well permeameter is used to determine things like soil, like water reuse. And the pilot infiltration test is commonly used in Washington. It's actually a pretty large test. So here's how they work on the computer. You can see these are the steady state techniques. They all assume a one-dimensional infiltration rate. One-dimensional infiltration doesn't really seem to be happening here. It is two-dimensional. The double ring infiltrometer, the well permeameter, and the pit test all have two-dimensional, actually three-dimensional infiltration, but they all assume one-dimensional infiltration, so they should have some bias. Here's what they look like after 6 hours, which is how long you're supposed to run these, 6 hours.
John, my apologies for the interruption. About 3 minutes, please.
Okay, thank you. I'm just about done. And this is what the other techniques look like: the TurfTech, the MPD Infiltrometer, and the saturated, and the Satiro. So a summary of the measurements. A KS measurement does not depend upon soil moisture. This is a good thing. If you have wet soil or a dry soil, you get the same saturated hydraulic conductivity for all of the infiltrometers, except for tight soils like silty clay and sandy clay. There is bias, but it tends to be constant. So that means that each infiltrometer has a certain bias. The exception is the TurfTech device, which doesn't really do that much in terms of the soil. It is really not accurate. We don't recommend it. The main difference is measurement time. So this is the observed response. The Turf Tech for this one case has a high bias factor, and it varies between 6 and about 2. The MPD has a constant bias factor. The Satiro has a constant bias factor. These all have a constant bias factor, which is a good thing. You just take your measurement, divide by the bias factor, and you get a true saturated hydraulic conductivity. The difference is how long it takes to measure. The falling head techniques are the first 3 here. The Turf Tech, MPD, and Satiro are falling head techniques. The double ring infiltrometer, well permeameter, and pilot infiltration tests are steady state techniques. You have to wait at least 6 hours to get steady state. That's the requirements. These 3 here can be as low as 30 minutes, 19 minutes, and 2 hours. For most of our infiltration practices, that's pretty close. If you go to the clays, then they can take longer, especially the MPD. So some take-home messages. Well, infiltration practices are a great BMP because they can reduce combined sewer overflows. They reduce pollutant load to your receiving water bodies, and they actually help with extreme events. But we need to measure the infiltration. We can't just take it off of a soil texture chart, because soil texture is only part of what causes a rapid or slow infiltration. And there's roughly a 30% failure rate due to poor infiltration, which was uncharacterized. So synthetic runoff tests, I like those the best. They're the most accurate, and they are relatively inexpensive. If you cannot do synthetic runoff tests, then you need to measure infiltration with point measurements. To get within a factor of 2, you need 20 measurements, a factor of 3, 10 measurements. Depends upon how important it is for you to get accurate infiltration measurements. Infiltrometers have a bias, but we figured that out. It's constant with soil moisture. It doesn't change when you change your soil, and you just divide by the bias to get your true saturated hydraulic conductivity and get your true infiltration rate. And we recommend the Satiro and the MPD because they take less water, less time, quick installation, and you can take lots of measurements. So that's my talk. We can ask and answer. I'll answer some questions towards the question and answer period. Thank you for listening.
Thanks, John. Yes, please post your questions in the Q&A, not in the chat. And I believe you can also vote on those that have been posted. So if there's an important question, it'll raise to the top. So our next speaker is Todd Shoemaker. Todd is a water resource engineer with Stantec who loves to model on computers, not runways. He has over 20 years of experience in water resources, including watershed and stormwater management, hydrologic and hydraulic and water quality computer modeling, ravine and stream bank stabilization and floodplain management. He's created hundreds of stormwater models and selected thousands of curve numbers for compacted and uncompacted soils, and he'll be talking about the effects of compaction on infiltration. Todd, take it away.
Thank you. Appreciate the introduction. And let's get going here. Dr. Gulliver just mentioned soil compaction during his presentation. So I'm going to expand on that a little bit, and only not within infiltration basins, but further up in the watershed and how that may affect runoff. So accurately determining post-construction runoff is critical to long-term watershed management. Increased runoff rates and volumes lead to in-size streams, more sediment in the water column, and increased localized flooding. If we don't accurately predict runoff, we can't properly size downstream mitigation measures. So let's talk a little bit about modeling and computer modeling, or as some of us like to call it, the curve number game. Curve number method is from the NRCS, and it's a widely accepted method for calculating runoff. It includes relatively simple equations used to calculate the amount of runoff from a rainfall event. Curve numbers range from 30 to 100, with larger numbers indicating a larger runoff potential. The lower the curve number, the more permeable the soil is. And curve numbers are assigned based on soil properties and then classified into what are called hydrologic soil groups. There's A through D. So A are sands, and they represent a lower CN or less runoff. And then hydrologic soil group D are generally clays, and they have a higher curve number or more runoff. So you can see here on the screen, the curve number for single family residential is technically lower than that for row crops for type B soil. So does that mean that rate control can be satisfied just by development? Is that really an accurate representation? This is a subdivision that went from undeveloped in 2016 through near completion in 2019. It's generally accepted that construction activity reduces the amount of topsoil via stripping and export and increases soil compaction by grading and stockpiling. This leads to increases in soil bulk density and decreases in the effective soil porosity. These changes to the soil properties then increased runoff rates and volumes. However, the amount of compaction that has occurred during this time and the corresponding change in runoff is not widely understood. So we started with the Minnesota Stormwater Manual. The manual does a good job of explaining soil compaction in terms of bulk density, but we hit a roadblock as we were unable to correlate the increase in bulk density, the decrease in porosity to an increase in curve number or an increase in runoff. Therefore, we shifted our focus to how those may affect the saturated hydraulic conductivity and how that changes due to construction compaction. This led us to the soil water characteristics calculator that USDA Agricultural Research Service created this calculator. And that's based on an equation derived from a 1,700 sample data set. It predicts soil characteristics based on these 5 parameters listed on the screen. The 2 that are underlined, organic matter and compaction, we underline those because those are the 2 main parameters affected by construction activity. So for a pre-development or the uncompacted condition, we use the calculator's default values to obtain saturated hydraulic conductivity for the 12 soil textures shown in the triangle. We then correlated that saturated hydraulic conductivity for those soil textures to the appropriate hydrologic soil group using the National Engineering Handbook. For the post-construction condition, we chose to simulate a moderate increase in compaction by going from normal to dense conditions. You can see in the list there that there's actually 5 compaction options. So we approached it from, at least our perspective, a reasonable increase going from normal to dense. That gave us still just that one change from normal to dense gave us some pretty significant impacts on infiltration. So we didn't want to go overboard to go up to hard or severe, but I guess just be aware that there are even more hard or severe conditions than what we selected. As I said earlier, many construction projects involve stripping, stockpiling, and replacing topsoil. This is important because topsoil contains most of the organic matter in a soil profile, and each of these construction activities reduce the overall amount of organic matter. So for our evaluation, if you recall back to that screen grab from the soil water calculator, the default is 2.5%. We reduced that by 2% based on input from some soil scientists in our office. All right, finally, we get to the so what. So drum roll. Excellent. Very busy table here. So what you'll see are columns of uncompacted information along with compacted soils. The left 3 columns contain information from the Minnesota Stormwater Manual. Kind of the middle 5 are information from the soil water characteristics calculator. Let's boil this down. And the top 7 soil types there basically all start in an uncompacted condition as type A soil. And as we work through the calculator, those saturated conductivities go from 4.5 or 3.6 to 2 to 2.7. So due to compaction, or really there is no change to that, there's minimal change to that soil type, to that hydraulic conductivity, or that saturated hydraulic conductivity due to compaction. As we move down, we look at this sandy loam row that started as A, but gets reduced from 1.99 to 0.82. So for that particular one, in an uncompacted pre-development or existing condition is type A soil, but in a compacted or developed condition, that should be considered as a type B soil. For the bottom, about the bottom half of this table, those are B, C, and D soils in the uncompacted condition. But then when construction activity occurs, the decrease in saturated conductivity is quite severe. So those should actually be modeled, or they're acting as a type D soil. All is not lost though. Don't lose hope. There's always hope, right? Several methods exist to mitigate compaction. There's tilling, soil ripping, soil amendments, compost amendments, and actually time. Soil or compost amendments are the most effective methods to immediately restore to the pre-construction condition. These are generally done towards the end of the construction process. Time and natural processes can nearly mitigate soil compaction, but as you can imagine, they take a long time, take many years to loosen up the soil, and after that time, it really only loosens the top 1 foot or so of the soil profile. And why that's important is a lot of times compaction is going to extend down to 18, 20, 22 inches deep in the soil profile. So how about implementation? How can we kind of wrap this up? We have on this table, you see land cover on the left side, pervious or impervious, then pre-construction, and then post-construction. So in the pre-construction condition for pervious, we're going to assign curve number based on land cover and soil type, much like what everybody does today. Impervious gets curve number 98. For a post-construction condition, if the pre-construction soil group is A, it's going to remain A, except for sandy loam. If the pre-construction is sandy loam, then that's going to use soil group B in the post-construction condition. For all other soil groups or soil textures, then those pervious areas would be assigned soil group D. For the impervious areas, obviously, if it starts impervious and remains, that stays with curve number 98. If it is converted to pervious, though, it starts impervious in a pre-development condition, and then that gets removed and it becomes pervious, then because there's already compaction there, that pervious gets assigned soil group D. If there are amendments, though, we're going to take that into account. So gravel, sand, loamy sand, no adjustment. That's going to starts A, stays A. Sandy loam, if you recall, pre-construction, that was A, post-construction B. If it gets amended, then that goes back to A. All other soil textures, if you recall, they start B, C, D, post-construction D. If there's an amendment, then it goes up to C. Let me conclude here real quick with a theoretical application. Let's consider a 10-acre residential development, type B soil. It's going from row crop to residential. For simplicity, let's just assume the time of concentration doesn't change. What you'll see in the table there is this curve number adjustment that I'm calling. I guess we kind of affectionately refer to it as the no bump. You know, you just keep the soil groups the same, or a bump where you actually change or adjust that soil group. So what you see there going from existing to proposed is that there's actually a decrease in the runoff rate and volume. When you look at that for the 2-year storm event, though, start comparing existing to proposed. For the 2-year, you have almost double the rate and volume when you're comparing the bump and the no bump situations. This is important because a lot of times that 2-year storm event is closely related to the channel protection volume or protecting downstream creeks and waterways. So if we think that we're managing our water well enough to protect from downstream erosion, but actually there's more water coming through the system, we may not actually be accomplishing that protection. Similarly, if we look at the 100-year, those rates and volumes are higher, as we would expect, than compared to without the bump. And this is critical because a lot of our ponds and basins get designed to manage up to the 100-year storm event. Not only that the pond may start overflowing more frequently, but also low floor elevations are a lot of times assigned based on that high water level. So if the high water level calculated might be a little low, then maybe we might start having more impacts to low floor elevations.
Sorry for the interruption, but if you could, wrap up, thanks.
Yep, just to quickly summarize, there's a general acceptance that soil compaction increases and thereby reduces the saturated hydraulic conductivity. There are ways to account for this in your hydrologic models, and a best practice is to certainly encourage soil amendments to try to mitigate for those. Quick thank you to Eric, my colleague, as well as Luke from CAP Region for help on the study and the slide deck preparation. Thanks a lot.
Thank you, Todd. So we're going to keep moving along here. Our next presentation is on the topic of addressing rapid infiltration soils, and we will have 2 presenters splitting this one, Noah Czech and Mike Gerber. Noah has been the City of St. Cloud Stormwater Compliance Specialist for 15 years. He oversees implementation of the city's stormwater pollution prevention program and surface water management plan. He's worked on implementing numerous water quality improvement projects and oversees the city's stormwater inspection and maintenance program. Mike Gerber is a civil engineer who works at Design Tree Engineering and Land Surveying, a multidisciplinary consulting firm. He currently is a project manager who also designs and drafts projects on a variety of different projects. Mike designs stormwater management practices and dealt with a number of projects where infiltration rates are higher than the rate designated by the regulating agency, the Minnesota Pollution Control Agency. So I'll let the 2 of you take it over, and Noah, I believe you're up first.
Yeah, thanks, Mike. Mike Gerber and I will be talking about how we have addressed rapid infiltrating soils. I'll be coming at it a little bit more from the regulatory perspective, I guess, as a city, and also as the implementation side on city projects. And Mike will dive a little bit further into how he handles things on the private consultant end of things and working with private property owners and communicating that regulatory requirements between the owners and contractors. It's kind of with that, the state construction stormwater permit in Minnesota prohibits us from constructing infiltration system in areas where infiltration rates are field measured at more than 8.3 inches per hour, unless the soils are amended, right? So if we test and are above 8.3 inches an hour, we're either not infiltrating that location or amending those soils to get below that 8.3 inches per hour. The permit also states when soil borings indicate type A soils that we should perform these field measurements to verify the rate is not above 8.3 inches an hour. So in St. Cloud, we've been implementing probably for about the last 5 years or so the following table for soil borings and infiltration testing in proposed infiltration treatment practice locations. And this is occurring pre-permit approval to confirm soil types and infiltration rates. The reason that we started implementing this was actually because we're having issues with projects at the design phase and just using soil borings as an indicator and getting in the field during construction, our sites were not infiltrating as we thought based on soil borings. They were actually infiltrating slower and kind of failing in that aspect. So we implemented this requirement to kind of help with that, which it has, but it kind of had the flip side effect of now we know which sites are field measured at 8.3 inches or above, and then thus having to amend the soils. So in St. Cloud, we have lots of good infiltrating, rapid infiltrating, sandy soils. So this has been something we've had to then deal with on the rapid infiltrating soil side of things. So, you know, kind of where did we start? Of course, the Minnesota Stormwater Manual has excellent guidance and a framework and a process put together of how, you know, where do you start? What are some options? What are some tools? How do you approach this once you know you're at above 8.3 inches an hour infiltration rate in an infiltration system area? So an example project of the city, this is a neighborhood improvement project, street reconstruction project that was proposed to install several underground infiltration chamber systems where we had rapid infiltrating soils well above the 8.3 inches an hour. So what we did is we took out those rapid infiltrating soils underneath the practice, mixed them with some other on-site soils that were not as rapid infiltrating, some silty sands, to kind of make a dirty sand, essentially slow that rate down. We didn't use in this project MnDOT topsoil or compost, which is one option or tool in the Stormwater Manual as a suggestion. We kind of felt this was the best approach, use some on-site soils that weren't as rapid with the rapid. We mixed on the side of the trench, so we did not mix this right in the trench below the chamber system. We did this kind of on the side, kind of a scoop at the time, lack of a better way, till it passed our eyeball test of what did it look like. Do you think it's going to be lower than that 8.3? We then tested the mix, another infiltration test, to confirm that we kind of slowed that rate down, but we shot for the high end. We wanted to stay more on the high end before we then installed this under the treatment system, I think at about a 12-inch depth on this project. One more real quick example, somewhat of a similar approach, but different on surface infiltrating practices, unlike an infiltration basin or rain garden. What we've done is we've replaced the rapid infiltrating soils with about a 12 to 18-inch depth of one of the soil mixes from the Minnesota Stormwater Manual, to kind of address not only the rapid infiltrating soils that were maybe above the 8.3 inches an hour, but also promote that plant growth and pollutant capture. With that, I'll turn it over here to Mike Gerber to kind of chat about his perspective on dealing with rapid infiltrating soils from kind of the private end of things and his work.
Yeah, appreciate it all. So I'm going to use kind of a case study from a project that we did in St. Cloud kind of as an example for this. And I'm going to start with the specification verbiage. We really only include these 3 bullet points in our specifications regarding infiltration rates. And it's basically, the first one is that the infiltration rates shall be determined by a double ring infiltrometer. The second is any variances need to be brought up to the engineer, and so that if any modifications to any of the BMPs need to be made, we can make those adjustments. And the third is regarding the maximum infiltration value. And we purposely leave these vague for a reason that I will get to kind of as we go through the example. So this example is a parking lot reconstruction project. It was a big enough redevelopment project that it triggered the city's stormwater management requirements. And the practice was actually located down in the southeast corner. So this is one of the typical soil borings that we got. And you can see that most of the underlying material underneath that fill section, which was the pavement section, was SPs with very low blow counts. So we anticipated that infiltration wouldn't be an issue, or too low of infiltration rates wouldn't be an issue. But once we got into construction, we proposed this offline infiltration, underground infiltration system. And once we got into construction, the initial field tested infiltration rates were about 100 inches per hour. And what we did was we just had the geotechnical consultant start with their double ring. And once it was apparent that it wasn't going to meet our specification, we had them stop. And we started with just a small section of soil corrections down. We actually did it in the trench, and we did 6 inches of topsoil that was available on the site with 6 inches of the in situ SPs, and they just bucket blended it down in the trench, and that got us down into about the 50 inches per hour range. So we ended up going with 12 inches of topsoil material and mixed in with 12 inches of the in situ sands. And this brought the infiltration rate down to the specified rate. And the reason we used the topsoil mixture on the site was because it was sandy, and it was really the only material that was readily available. So that's kind of a big piece of it. And that's kind of why we leave our specs vague, and we just communicate with the owner up front that, you know, this could be a possibility, but there's really no way to plan it until we get into and have our tested values. So it's a function of material availability and the kind of risk versus cost analysis and how we go with this. But as we do more projects, we're able to kind of get a little bit more knowledge of what depth of what certain types of media that we need to blend. And that's how we approach projects. And it's a big communication exercise and coordination between the owner, the consultant, and the contractor. So that is all that I have for my example. I'll pass it back to Mike.
We'll keep moving along here. So our next presentation is on infiltration at contaminated sites. Again, we have a tag team effort. 2 speakers, Eric Lund and Forrest Kelley. Forrest joined the Capital Region Watershed District in 2007 and manages the Watershed District's rules and permitting programs. He assists permit applicants, coordinates site plan reviews, and makes approval recommendations to the Board of Managers. He also manages the capital improvement projects to help protect the water resource of the district. He holds a BS in Biosystems Engineering from the University of Minnesota and is a licensed professional engineer. Eric Lund has more than 15 years of environmental engineering experience, currently working with Barr Engineering. He manages and consults on projects across a wide array of environmental topics, ranging from the investigation phase through evaluation of remedial alternatives and designs of remedies for contaminated sites. He also manages large-scale dredging projects along with the investigation and closure of urban landfills and dumps. Eric's work often involves building multidisciplinary teams to leverage the breadth of experts at Barr Engineering. So with that, I believe, Forrest, you're up first, and take it away.
Yeah, thanks, Mike. So we all know dilution is a solution to pollution. All right, that's it. See you later. No, it's not, but I do want you to keep that phrase in mind as we go through this presentation here. And though it isn't the solution, we all know it's not, because otherwise we wouldn't be here sitting talking about infiltration. So what I will be going through today, if I can advance my slides here, is how we took a light industrial property like what you see here with garbage trucks, street sweepers, vac trucks, into something that we all work in, staff of 23 at CRWD. And you can see the picture on the left is some before, and the picture on the right is the after of how Capital Region successfully transformed a municipal repair equipment shop and garage into our office. So before I jump into that, I wanted to just give a little bit about Capital Region. We're a special purpose unit of local government tasked with protecting, managing, and improving our water resources. 41 square miles of area around the capital. St. Paul, Roseville, Maplewood, Falcon Heights, and Lauderdale are our member cities. We got about 1/20th of the total population of Minnesota living in CRWD. We've got 5 lakes, and 42% of our area is impervious surface, making us the most highly urbanized watershed district in the state. So back in 2016, Capital Region purchased the former McQueen equipment property to repurpose it as our new office. We set some goals of creating a sustainable workplace to conserve natural resources, practice what we preach in protecting water resources, and really create a demonstration piece for the public to come in, engage with stormwater education and the natural and built environment. So we hired MSR Design and EOR on the architect and civil side of things, and we set some high goals of having a variety of stormwater practices that you see here. These are all the practices that were implemented, and then we also set ourselves a goal of trying to achieve our regulatory standard, even though for this portion of the project we were not required by the city, NPDS, or our own rules to do that. We wanted to treat the 1.1 inch, and we were actually able to achieve over the entire site, which includes 2 parcels and 2 buildings, about 2.5 inches of infiltration storage. However, we knew going into this that we might come across some issues, and indeed, some issues were identified that made infiltration initially deemed infeasible. So we engaged Barr Engineering to work with us on the environmental engineering side of things and create a response action plan for construction. And during that analysis, it was identified that the building had asbestos, lead, there were solvents underneath the slab, so there's vapor concerns. And then what we're going to focus on today is previous tank releases from some underground storage tanks that impacted the soil and the groundwater. So the general permit does say that infiltration is prohibited where high levels of contaminants or groundwater will be moved by infiltrating that stormwater. And there is a guidance tool to try to provide some direction. But we took it a step further with engaging Barr. And then we were really posed with the question, what should we do? We really wanted to try to provide some infiltration on the site. Typically, if there's a site with contamination that goes through our permitting process, they are jumped into alternative compliance sequencing where we're utilizing lined filtration systems, whether it's bioretention or underground or manufactured treatment devices. But we started thinking, well, what if we infiltrated relatively clean stormwater into the groundwater? What would that look like? Would it be beneficial for the groundwater in that area? So at that point, we took that question to Barr Engineering and re-engaged them to conduct additional analysis and amend our response action plan with the MPCA. So with that, I will engage Eric for the rest of the presentation.
Okay, thanks, Forrest. We appreciate the opportunity to work with Cap Region on this project, and happy to be here with you all today. So, as Forrest said, we're looking at how can we achieve this infiltration goal given the site conditions, and what happens if the best spot to infiltrate is right where the contamination is. And that happens to be the case on this site, where the southwest corner, the low spot, the down gradient end of the site where we wanted to sort of collect and infiltrate water happened to be where some old leaking underground storage tanks were, and when there was some residual petroleum contamination. Next slide, please, Forrest. So in this situation, MPCA would typically suggest you can either move the feature, you can modify the feature, or you can model and demonstrate that there's not going to be a negative impact. And that's the route that Cap Region wanted to go. So we installed 4 permanent monitoring wells. We collected soil and groundwater samples to better characterize the geologic and hydrogeologic conditions and the contaminant concentrations. We calculated hydraulic conductivities, and we did all this, next slide please, Forrest, to construct a groundwater model that we could use to evaluate the impact of the infiltration. So Forrest alluded to the mounding calculator, sort of the simplified approach the MPCA does include in the Stormwater Manual, where you look at basically how high is the groundwater table going to rise as a result of infiltrating stormwater, and does it have the chance to intersect with contaminated soils or groundwater, and all for the purpose of not making an existing condition worse. So we used our groundwater model, and we're fortunate at this site for this perspective of having pretty sandy, poorly graded sand soils. And so the mound that forms is actually relatively small and dissipates really quickly. So our contours on this image are showing 0.2 of a foot is basically what we would measure around our infiltration base. And I think the maximum mound was less than a foot right through the center. So we said this is a positive. We're not intersecting some existing contamination. Groundwater here is down at about 35 to 40 feet. So we're below sort of these former tank basins. So we thought that was a good outcome. Next slide, please. We'll look at the second piece that we used our model for, which was the sort of contamination transport. And so a lot going on this slide, but the left-hand side is existing conditions and the right-hand side is modeled future conditions. And so we modeled petroleum contamination conservatively as benzene to use some of those transport mechanisms. And petroleum has the benefit as a contaminant of some natural degradation. So you can see on the left-hand side, our groundwater flow is taking the contamination to the southwest. And those are sort of concentration gradients. It's going offsite, but not too far. And so then we looked at, on the right-hand side, what if we increased that recharge rate via infiltration and supplied, oxygen-rich stormwater? Does that actually potentially have the effect of improving the contaminant condition? And the model would suggest that it does. So by adding that extra, that oxygen, we can basically start aerobic degradation or enhance it. And we show the benzene plume sort of shrinking in this scenario. Next slide, please. So then we continued our collaboration with MPCA, started using this term beneficial infiltration, the potential to improve the condition because of increased loading. And our model suggested that infiltration doesn't change the flow direction, a minimal mound develops. And we had, generally MPCA support with some caution, because there are other sites in the area. There's a down gradient Superfund site, and you need to consider sort of associating yourself with other contaminants. Next slide, please. So we installed the feature, during construction. We ran into some additional contaminated soil, additional storage tanks, but things that we were able to deal with. Next slide, please. And then we started a monitoring phase. And so the first image here is relative groundwater elevations. And so what we discovered was the general direction of flow from northeast to southwest didn't change. We didn't observe a large mound beneath the infiltration practice. The groundwater table sort of fluctuates with precipitation, as you might suspect. And so, I kind of confirmed our model there. We looked at the contaminant side as well, kind of how the petroleum concentrations changed potentially as a result of the infiltration. We observed some initial relatively small increases. We have some theories about that being potentially related to sort of stirring up some of that impacted soil during construction or fresh paving. We saw those come back down, and they weren't at a level of concern that made us sort of worried about the impact that we were having. And they're much lower than we observed in that initial tank basin sample. So what we learned was, there wasn't a change to the flow direction. We didn't observe a large mound. We saw some minor increases in that petroleum concentrations initially, but subsequent reductions. And we really viewed this as a successful infiltration on a contaminated site. From the regulatory side, the leak sites are closed. MPCA accepted our response action implementation report. And so things are going well. They're in sort of operation mode now. There is a bit of caution on the next slide. We talk about that, the risk isn't zero. The type of contaminant, the concentrations really do matter, right? This is a relatively lightly contaminated site. Petroleum is a better contaminant, I guess, for this perspective than, say, something like a PFAS or a chlorinated compound that doesn't want to degrade as easily. Monitoring and modeling really are helpful in making these decisions as to the appropriateness and the risk management. And MPCA involvement on our project was really key to kind of give us the confidence that we could do this. I'll pass it back to Forrest for just a couple of images. Thank you.
All right, thanks, Eric. So as Eric mentioned, we deem this as a success, and overall, really happy with the building and the stormwater practices that we've implemented here. We did move in December of 2018. We are monitoring the underground infiltration system in the southwest corner of the property, and have observed no stormwater discharge from the site, from the area of the site that does drain there. And in 2023, we're going to re-engage Barr to help kind of transfer the responsibility of monitoring over to our in-house monitoring staff, so that we can continue to take samples from those wells and ensure that we are continue to have a benefit to the underground, to the groundwater system, and are not moving plumes or adding pollutants to it. So with that, I will say that while dilution may not be the solution to pollution, physical, chemical, and biological processes to reduce petroleum hydrocarbon pollution and local superficial groundwater may be the solution to the pollution. And that's all I got.
Thanks, Forrest and Eric. Okay, saving the best for last. Well, John, you owe me a $10 bill for that. Dr. John Nieber will be talking about potential groundwater impacts from stormwater infiltration. Dr. Nieber is a native of upstate New York and received his BS in forest engineering at Syracuse, his MS in civil engineering at Cornell, and a PhD in agricultural engineering at Cornell. He would join the Department of Agricultural Engineering at Texas A&M in 1979, and in 1985 saw the light and came over to the University of Minnesota and joined the Department of Agricultural Engineering. In 1995, he was promoted to full professor, and John's research interests involve hydrologic process discovery and modeling, with a particular interest in flow and transport processes in porous media. He is a member of the American Society of Agriculture and Biological Engineers, American Geophysical Union, Soil Science Society of America, and a certified professional hydrologist with the American Institute of Hydrology. His current research involves studies on utilizing infiltration for stormwater control in urban areas, assessing best management practices, impacts on reduction of nitrate in groundwater, and combining hydrologic models with machine learning and quantifying mass and energy transport processes in urban ecosystems. So with that, John, take it away.
Well, thank you, Mike, and Andy too. So I'm going to talk a bit about the result of some work that we did and published in 2014. So it's a while ago, but I think the results are still valid today. And of course, new updates are probably something that should be done. But I would like to refer to this report that's given at the end of the presentation. You'll see the citation for it by Nieber et al. And I want to give a special credit for that to John Gulliver, Pete Weiss, and then to Brian Davis, who's at the Met Council, because the work was done under the auspices of the Met Council. So there was interest in, as you saw in the last presentation, interest not only in using the infiltration features of the ground to be able to control stormwater, but also there's concern about potential impact of that stormwater reaching the groundwater with contaminants. And it might be because of an infiltration practice, or as Michael was saying earlier, it might be just because you're using stormwater and infiltrating it for, let's say, managed aquifer recharge or something like that. So, the situation is kind of summarized here. I took this from an article by Tindoli in 2016, and it shows water coming into, or give the idea of contaminant influx into a infiltration practice with possible overflow, and then plant uptake of both water and nutrients or contaminants. Retention of the contaminants in the soil as the water infiltrates into the soil, and possible downward flux deeper down to shallow groundwater. And there's this summary gives you an idea as to just some characteristic concentrations of some different types of contaminants, both nutrients as well as heavy metals and petroleum products ending up in stormwater. And so total suspended solids, total phosphorus, cadmium, copper, and as I said, some form of petroleum product. So this just gives you an idea of what some median values are. Obviously, they're going to vary around the country, but give you an idea as to what concentrations have to be handled in these stormwater practices. So the effectiveness of BMPs on removing these contaminants is going to be dependent on a number of different factors. It depends on what the contaminant is. If it's bacteria or something like that, total suspended solids, then the filtration effect of the infiltration material is going to be important. So particle size distribution of the infiltration material of the porous media, and then also, of course, the particle size distribution of the contaminant itself. The absorption effect is going to be affected by cation exchange capacity of the media, which not necessarily a constant, may be affected by the pH of the liquid mixture with the media. And it also depends on the buffering capacity of the media as to whether it has sufficient buffering capacity so that the pH doesn't change a lot. Wettability of the porous media is very important because if it's not very wettable, water will move past the porous media. You won't have good contact between the media and the contaminant. Magnitude of infiltration events is also important because that's going to determine what the rate at which the water is being driven into the soil or into the infiltration practice. And that, of course, is going to affect the residence time of the liquid in contact with the porous material. And that we know is going to influence the effectiveness of uptake of contaminants and maybe absorption or even biodegradation of contaminants. And then a really important one here is a presence or absence of preferential flow phenomena, such as the presence of macropores, unstable flows, finger flow, as they might call it, in the porous material, or some sort of heterogeneity-driven flows that leads to unstable flows as well. So all these things are important factors, and I'm not going to get into any of the details of how to model any of these things. Those are things to be discussed at another time. But I'm going to talk about the monitoring that we did here in the Twin Cities metro area. And I will as soon as my slide decides to move. Okay, there we go. So we were contacted by the Met Council by Brian Davis to put together a proposal to study the contaminant movement in infiltration practices. We searched around and found three practices that we could, three locations where we could do this, and they're located here or indicated here on the map. Location A, which was a rain garden located right near the Como Park Zoo, right on Hamline Avenue, and then location B, which is what's called the Beacon Bluff underground system, and that was a site where there had been quite a bit of industry in the past and is being converted over to a more recreational area, and an infiltration pond was put there, and then sheep pasture infiltration basin, which is point C, location C, and that's at the University of Minnesota St. Paul campus. I'm going to talk just briefly about each one of these. So the location A, or site A, which is the Hamline Midway rain garden. You can see it on the right-hand side, an aerial view of it. The zoo is located just to the right of where the rain garden is located. And we put in sampling bottles, lysimeters at this site to be able to collect samples of runoff that's collected in the rain garden, and also then to sample the water that's infiltrated into the profile. There's a cross-sectional view of these samples. So we had suction samplers, and we also had open bottle samplers that allowed water to enter in, and we could take those samples and do analysis of them. The site B is, this is illustrating the purple area that you see is the contributing area to the Beacon Bluff infiltration system. And the Beacon Bluff infiltration system is located down in the light blue area that you see in the bottom of the diagram. And at that Beacon Bluff site, what they did was to put in, excavate a large volume of soil out and put in some granular soil, or granular, basically just sand, and then shredded tire chips was put in as a layer within it. And the volume of water that from runoff would go on the surface, as you see it there. It's kind of green, grassy area on the top. And then also, if infiltration event or runoff events were large enough, water was diverted over, rather than having the pond overflow, water was diverted into those circular cylinders in the bottom, which were perforated culvert. Then on top of that, then there were samplers that were inserted at the different depths that are indicated there by those vertical lines. And those were just open barrels. And I guess I've got it on this next picture that illustrates that. So you get a side view showing the perforated pipe, and then these open, basically 50-gallon drum barrels that were cut in half. And then there was a pipe inserted into there. There was gravel put inside each one of these 50-gallon drums, and the pipe then protruded back to the surface and allowed us to take water samples from the water collected in each of these barrels. And of course, water would enter into those barrels because water moving down by gravity would reach those barrels and then infiltrate into the gravel that's in the top of the barrel. And these were at the various depths that are shown there. The last site is the one at the University of Minnesota campus, St. Paul campus. It's the agricultural campus. And so there's this pasture area just to the south of this. There's 2 roads there that are indicated as paved areas there. And just to the south of that is where the state fairground is located. So we had runoff coming from parking lots, runoff coming from the sheep pasture, the manure on the site, and so on like that, because they had horses out here and all that kind of thing. And there was a composite site, compost site just to the north. And so the water infiltrated then into those basins. The kind of pink arrows that are shown there show the where runoff is coming into the basins, and then the blue arrows indicate how water would move around in those basins as a result of changing water levels. We can get water standing in there 4, 5, 6 feet high during a big rainstorm event. All right, so this gives a summary. I'm not going to go through the details here. I know that these slides are all going to be published in the video and also separately. So if anybody's interested in seeing what kind of samplers we had, this gives a summary of the sampling pools that we had for Beacon Bluff, Hemlin, Midway, Rain Garden, and then the sheep pasture. All right, so just to give you an idea as to what the results look like, this was done during the period 2012 to 2013, and took about 155 samples total. These were analyzed for nitrate, chloride, total phosphorus, cadmium, a number of different metals that I'll refer to. So cadmium, lead, iron, and so forth. And then also for the Beacon Bluff site, we also looked at the total hydrocarbon content in the samples. And located on each of their, indicated on each one of these graphs is the MCL for each of these contaminants. For the total phosphorus, there's no MCL indicated because there is no standard for that. There are water quality concerns about it, but there's no health standard for the total phosphorus. So we can see there are some exceedances of the MCL for the chloride as well as for the nitrate. For the total phosphorus, as I said, there's no exceedance, but these concentrations are well above the levels. Let's say a lot of them, let's say for streams in Minnesota, the concentration we get concerned about is would be 100 micrograms per liter. And then for lakes, it would be anything maybe between 40 and 60 micrograms per liter. So if this is going into the groundwater and eventually ending up in a stream or discharging directly into a lake, it could be a problem because it would then lead to algae blooms.
John, pardon the interruption, but about 3 minutes, please.
2 minutes. I only gone 7 so far.
3 minutes.
Okay, thanks. Then here just, I'm going to go through these because I only got a little time left. And like I said, these slides will all be available to you if you want to look at these later. Just give you an idea for chloride, there was exceedances of about 15% of the time of the MCL. For nitrate is about 8% of the time. Total phosphorus, there's no exceedances because there's no MCL. Then for the metals, of course, there's no MCL for iron. There is for lead, and you can see there's some exceedances there. But for all the other heavy metals, there were no exceedances of the MCL concentration. There is none for nickel, which I didn't show the slide for that, but nickel didn't have any exceedances either. For the iron concentration, I show an MCL, but actually that just has to do with water quality and not necessarily for health effects. And then for lead, the exceedant was about 4% of the samples had exceeded the MCL for lead. There might be some interest in knowing whether there's an effect of concentration with respect to depth, but we didn't find anything that was consistent there. The correlations were very low, and in the case that you see for the nickel on the right-hand side, there's a positive increase in concentration with depth. That's not really expected, but that's what was found here. And their R squared was pretty good for this, but still, it's not what we would have expected. You expect higher concentration near the surface where there's more organic matter. And I'll just mention here about the TPH that was only done at the Beacon Bluff, and what was coming into the runoff into the infiltration practices circled there or indicated by the box, the red box, both in May of the year and then in June of the year. These are just two different events, and the thing is that we don't find any correlation between the TPH and the concentrations that are at depth, and there's going to need to be more work done on this. So since I have to hurry here, I'm going to just give my conclusion. And so as I've already mentioned, chloride concentrations were exceeded about 15% of the time for the MCL. Nitrate was 4%, lead was 8%. And then copper, chromium, nickel, and so on, there was 0% exceedance. For total phosphorus, there was no MCL, but they were very high values. Depth dependencies were poor. Most of the results of the study are consistent with results that are reported in the literature, and that manuscript or that report that I refer to is a good one to look at because there is an excellent literature review done in there by John Gulliver and Peter Weiss. And then, like I said, the TPH results were not conclusive. So some recommendations for further study: need additional work on TPH as our results were not conclusive. Removal of bacteria microbes was not studied here. There's been a lot of work done on that in laboratory studies. I think there needs to be work done also in the field. It wasn't done here, so I think that's something that should be looked at. And there is concern about viral cells. That was not looked at here as well, and that's something that probably should be done in the future as well. So I'll leave it there. Here's the reference from, like I said, it's from 2014. That's not.
Thanks.
Yep.
Thanks, John. So we threw a lot of stuff at you today. If I believe, John, do you need to stop sharing so that I can share? Yep. I'm not sure how Zoom works. Got all these different platforms for an old guy like me, and it gets really. So I am just going to real quickly go. I did scan the questions very quickly and came up with 3 general questions that I believe I can answer regarding my little piece here. The first is, what's in the manual? And if you go to the Minnesota Stormwater Manual and you go to this page called Stormwater Infiltration, you'll see all kinds of stuff there. Overview, best management practices, information on water quality, including groundwater impacts, groundwater mounding, what are the effects of different potential constraints like contaminated sites, wellhead protection, karst, so forth. Decision tools, determining soil infiltration rates, which Dr. Gulliver covered. We have a whole page on soil. If you went to that page here, you would see that we've got a lot of pages in the manual on soil information, general information and tables, and this would include things like curve numbers and so forth. A section, a couple pages on chloride references and so forth. But another question that kind of came up as a general theme was, will the manual be updated as we gather new information? And of course, the answer to that is yes. A couple things I've heard today caused me to think, well, maybe we need to go back and revisit some of the information in the manual. So yes, we're always open to suggestions, and our ears are always open and amenable to updating the manual with the most recent information. The third theme that I saw in the questions was, well, what don't we know? And I just threw together this list. I just posted it here for today's webinar, but some of the things that pop in my mind are, what are the long-term effects of perennial vegetation and soil biology on infiltration and stormwater practices? This whole concept of dynamic infiltration, I know the Villanova folks are looking at this, and I believe Dr. Bridget Wadzig was a speaker a couple of years ago on this particular topic, and John Gulliver touched on the three-dimensional nature of infiltration and how we tend to look at it one-dimensionally. The effects of road salt and chloride. What are the effects of long-term maintenance on, and so we really have begun to stress design phase maintenance. When you design something, think about O&M when you design it, not after it's already built. What's the role of pretreatment and infiltration? And then potential groundwater impacts from infiltration in soils with limited organic matter and high infiltration rates, which was touched on in a couple of the presentations today also. So with that, I will stop sharing. So there's a lot of stuff in the manual. I would encourage you to go there. Feel free to contact me if you have questions and suggestions. And Andy, I'll pass it back to you.
Thank you very much, Mike. Yeah, all of our panelists, you can come back, turn your videos back on. We're going to jump into our questions. I want to thank everybody for not only attending today, but providing some really good questions in the Q&A. We will not be able to answer them all right now, but what I do is I actually copy these questions into a Google Doc. I share it with all of our speakers and panelists, give them an opportunity to provide an answer. And then everybody that registered for the event will get an email from me with a PDF of the questions and our panelist answers. So with that, we're going to dive in. Our first question, our most highly rated question. Again, if you see a question in the Q&A that you like, that you really want to have asked of our panelists, make sure and give it a thumbs up so it rises to the top and we can see it. The top question right now is, how important is it to insist on a maximum infiltration rate of 8.3 inches per hour? And that might be a loaded question, but anybody can jump in, and I'm looking for multiple perspectives on this. So what do people think about insisting on a maximum infiltration rate of 8.3 inches per hour?
I guess it depends. I'll come in here and say, I would like to know where that number comes from, because I am not familiar with that criteria, and I would like to know what kind of analysis has been done. Is because of, you know, when you've got that high of an infiltration rate, water's going to move so fast, you will not have good treatment of the waters that are moving through. So that would be something I would like to know. I think it's a very good question.
I think that a lot of these things, these numbers in these manuals, come out of the early manuals. For example, the Maryland Prince George's County Manual and things like that. And many of these numbers, like 8.3 inches per hour, you don't really know where it came from. I'm making assumptions at this point. So I have to apologize for the fact this is my assumption. My assumption is that the 8.3 inches per hour was determined based upon infiltration and underdrains. So if you have basically a biofilter, and then you put the water back into the storm sewer, you want to treat that water rather than just have it run through and back into the storm sewer. And it carried over into infiltration. And I haven't heard a good justification for it in an infiltration practice. But there are many practices that have both filtration and infiltration because they have an underdrain and they do have filtration. And I think that from that point of view, that could be where the 8.3 inches per hour comes from. I think that's a good question and we have to revisit it.
Other ideas or perspectives on the 8.3 inches? Go ahead, Forrest.
Yeah, I'll say that in terms of how important it is, we try to look at what the groundwater resource is that we're trying to protect. Within Capital Region, we don't have any drinking water source management areas. None of the groundwater aquifers here are used in such a manner that we feel infiltration should be completely restricted. So we also consider some of the impacts during construction. I think maybe there was a comment about compaction during infiltration during construction, and is that enough to slow the water down? We don't want to, we have to find that balance of prematurely aging the system by adding soil to slow the water down, and how it will naturally slow down as it begins to clog up from the sediment that is being filtered through the soil. So this is one that we struggle with. We don't often have a lot of actual testing data for the infiltration rates. A lot of times it's just soil borings. So I do think it is a good question to revisit.
Andy, if I could just jump in real quick. This is my perspective, not my agency's perspective. Although only being 2 months from retirement, I care a little bit less about that. I think when you can infiltrate the water and not have adverse impacts, I think you should infiltrate it. It's consistent with our promotion of green infrastructure. If you can infiltrate 10 inches per hour of clean water and not have impacts that are negative, I don't see why it shouldn't be promoted. That's just off the top of my head. We're promoting green infrastructure, but sometimes I think some of our regs or whatever get in the way.
Other thoughts? Go ahead, John.
But Mike, you use the key word clean water, or key phrase, infiltrating clean water, and stormwater is never clean. So, I mean, if it'd be different if it were treated wastewater, let's say, then you'd be able to say it's probably clean, but stormwater is never clean. So, I do recognize the need to maybe look at this upper limit, but 8.3, why 8.3? Is it maybe it's what John Gulliver said, that it's has to do with these under drains or something like that, but I think it's something worthy to take a look at, just because somebody asked, more than one person asked that question. Thumbs up to it, and I think it needs to be investigated. Give professors a little bit more work to do.
Any other thoughts before I move to the next question? Not seeing any. So let's dive into testing. So moving away from that criteria, when do you recommend taking infiltration tests? And this, I'm actually very curious to answer to this question, because I want to hear what the practitioners say from their experience. Have they taken it at different times and had different results or different successes? I'm also interested from the academic side and the research side. Do we have any evidence to suggest when a better time to take infiltration tests would be? And I'll add, the second half of the question was before planting in case the plants fail, or after the final stabilization, or at some other point in that planning, design, or construction phase. So what do we think about infiltration testing?
Well, I guess I'll start. I think the most important time to do infiltration testing is before construction. The thing that's going to slow your infiltration rate down the most would be what is underneath your engineered soil. And so if you've got a clay underneath your engineered soil, you haven't built infiltration basin, you built a pond. So you want to make sure that that soil underneath your engineered soil will allow infiltration. The engineered soil, it's really not a factor for the most part. If it's good engineered soil in terms of infiltration, it's really what's underneath it. And so I think that's probably the most important time. Post-construction, it's good to determine if the practice is still infiltrating, if it's clogged or not. That's always a good thing. And post plantings, it takes a few years for the plantings to actually develop root systems. And so post plantings is difficult, but the plants will always increase infiltration rates for the most part. There are studies being done at North Carolina State University with Bill Hunt, where he has shown that most of his rain gardens, most of his infiltration practices are increasing in infiltration rate over time. If you can get past that first initial stage where you first turn it on and you've got plants, they will keep the pores open.
Other thoughts on that?
Yeah, when I hear the question, I'm thinking maybe because I saw on the list of questions one had to do with temperature. So it may be, somebody says time, and John interpreted that to be before construction, after construction, before vegetating, planting, and so on. But maybe also there's a concern about, well, do I take it in the spring? What if my design really has to stand up for summer or for fall or something like that? Well, temperature does have a big impact, and because it affects the viscosity of the water. It doesn't really affect the density, but not very much. But the viscosity is tremendously affected by the temperature of the water. And so, I don't know if the time has, the question about timing had to do with that or not. I know it had, temperature was in one of the questions in the Q&A. So that is something that would be of concern.
Do you have a recommendation, John, on temperature wise? Is it better to test in the spring or the fall or the summer to be representative of how these things will perform, or we want them to perform? And that's open to anyone. Yeah. You mentioned temperature, but that's it. Yeah.
Mm-hmm. Well, I think to recognize that temperature is that important, one can, I think, I haven't done this before, but I think you could probably scale your measured infiltration rate that you make at a given time, knowing the temperature of the water. You should be able to scale it to whatever time that you really want it to meet the requirement by just changing the viscosity of the water, as a factor of the viscosity of the water. So I'm kind of skipping the questions.
That's okay. That's okay.
I'm avoiding the exact answer there, but I think that there's a way to get around that. I kind of like the approach that the interpretation that John had, because I think that's probably more important, before or after construction. Yeah. And then recognizing that when you do the planting, it's going to always benefit. And as the soil structure improves, you're going to have a higher infiltration rate than what you had when you first put things in.
But I think it is important to reiterate that the temperature when you're doing the test is important. So if you're taking measurements in October versus the middle of July, just recognize that that's not really an apples to apples comparison. So we can adjust for that. Other thoughts on or experiences or perspectives on when would you recommend we take these infiltration tests? What do you gain from it? And maybe you take them at different times because you get different pieces of information. What do our practitioners think?
I would agree that before construction is the best time to get the information on the soils so that you know whether or not you're going to have an issue once it's completed. It's sometimes hard to do, especially with these underground systems, but if an engineer and developer are willing to take the time and spend the money on doing that right before the system gets installed, that's, in my opinion, the best time to do it.
Considering what Todd talked about, and I know he wasn't specifically talking about a bioretention basin, for example, but I think it's really important also, if you take measurements before and not after, that you really take care not to compact the site.
And I'll maybe reiterate that it's good to set that benchmark as soon as that practice is quote unquote delivered, right? It goes online and it's meant to be in use. Are you getting the function out of it that you originally designed it for? And then also, I'm going to argue, take those tests over time. See how it's changing, see how it clogs up, because it could be compaction during construction. It could be fine sediment gets in there somehow during construction, or it could just build up with sediment, or will build up with sediment over time. So taking those infiltration tests at multiple stages can give you good information on the success, or hopefully ensure the success of these things. So the next question I want to dive into, it was addressed for Todd, but actually it does apply. There could be some good perspectives from everyone on this question. And the question is the state of Minnesota going to enforce the changing of the soil type for pre versus post-construction in stormwater modeling to account for compaction or certain soil types? And does anybody know if they're doing something like this in other states? Are they already using a standard like this? Are they thinking about going to a standard, or is there a different type of standard maybe other places are using that we should consider or emulate? So what do we think about that? That's a big question. Go ahead, Todd.
Yeah, sure. I'll jump in there. Regarding whether the state would enforce, I'll certainly leave that to Mike to comment on. But I think from my experience, it's really up to local agencies or local review how to accommodate for soil compaction, whether that's city, watershed, county review. A little bit more context is that this idea really came from some of our clients, our municipalities, watersheds, where their staff were receiving complaints about new development goes in and there are downstream impacts. The response is, well, we have stormwater rules. They met the rules. Yes, that's true. But also, if you think about the hydrograph, I think what the residents were probably seeing is just that hydrograph being stretched out, more water just running longer. So that's where the idea of adjusting the curve numbers came from. And instead of suggesting just a bump, just changing by one soil group, I guess we dove in a little bit deeper to see, well, is that right? Or how could we try to quantify that? So you saw in the results, type A soils, it's kind of a good thing. There's not a need to change that. Whereas the other soil types, perhaps there is a need. Regarding other states, I'm not familiar with that, but I can say, to be honest, we've given this presentation elsewhere, specifically down at the Iowa Stormwater Conference. And when we do have more time, we take a poll at the beginning of the presentation to see how many in the room are familiar with this concept, or how many already are adjusting post-development curve numbers. And many in the room down in Iowa are already doing it. Not necessarily to say this way, but it seems like it's folks are aware and recognize a need.
When I listened to Todd's presentation, the take home I got wasn't so much, well, let's change the curve number. It's what can we do to not have to change the curve number? And I think maybe that's what we should start thinking about, was when we develop a site, let's not compact it. Let's do what we need to make sure it doesn't get compacted. How that happens, you know, does it happen through regulation? Does it happen through education and outreach? You know, I think that's a discussion that needs to happen.
Other thoughts on that? And that's, you know, we can broaden that to soil amendment in general, right?
Yeah, that Mike's point of how to reduce runoff. Our goal when we're reviewing these plans is to get the soil amendments and the soil ripping onto the plans. We would prefer, while it's, you know, more accurate to model it that way, what we don't want is water washing sod away because there's just this thin layer of topsoil that makes the water gets through the sod and the topsoil and then just runs off underneath because that hard compacted soil is right there. So our goal is do the amendments, do the soil ripping, improve the moisture holding capacity of the green spaces on the properties as they redevelop.
Any other thoughts on that? So let's go to the next question. And I'm going to broaden this question. The question is specific in saying, were there any concerns or evidence of contaminants from the use of shredded tires? And I know I've heard that question from other projects as well. So we want an answer on that specifically, but I'm also going to broaden that to other amendments that we might put in our soil, in our rain gardens, in our filter media. Are there concerns or evidence of contaminants when using either recycled products like shredded tires or even some of our other amendments we typically use?
So that would have to do with the contaminants that are derived from the shredded tires themselves, right?
That's correct. Yep.
There is that effect. So I never saw anything brought up about that at the time when we were doing that project. I don't know, John, if you remember anything about that, but I do remember MnDOT having a call for proposals once about that. And I don't remember what the contaminants are anymore that will, let's say, change phase from being in the tire material to the liquid, you know, to water. But that's not something that we looked at all. And we didn't test for any of those, any contaminants that I know of anyway, that might come out of those shredded tires at the time. There might have been some contaminants associated with some of the contaminants we actually measured, but I don't think so. So, I mean, it'd be more organic, maybe.
If I could jump in there, it was either a week or two ago that that research is ongoing, and there was a presentation. It was a webinar, I think, sponsored by the local road research board. So I'm not going to bring up any results. I would just suggest people, if they're interested, to try to locate that and see what the research says thus far.
So my people presented, my postdoc presented the webinar. And so I can talk a little bit about that. I don't want to talk for too long because we've got a lot of questions here. But we were doing batch studies with multiple flushes on tire-derived aggregate, which are these shredded tires. And we found that the tire-derived aggregate actually absorbed phosphate out of the water. So that's a good thing. It absorbed phosphate, which is a important pollutant in Minnesota. But also we found that it leached zinc, iron, and copper. And then we did a second study that was funded by MnDrive. And then we did a second study funded by the local road research board. And we thought about, well, what about these biofilms that grow on the TDA, on the tire-derived aggregate? So we did a study where we grew biofilms on the tire-derived aggregate, and we found that the biofilm, even a thin slime layer, was enough to capture the metals. And it didn't affect the ability to absorb phosphorus. So in terms of metals and phosphorus, everything's good with this tire-derived aggregate. Now, in terms of other compounds, like 6-PPD quinone, I don't know. And there's a study going on to see if that affects Minnesota fish. That's the compound that affects from tires, it affects the salmon in the Northwest. But so far, everything looks good.
Would there be those biofilms form on in an unsaturated material? Like, in this case, the tires, shredded tire material would be unsaturated.
Yeah, we left it unsaturated for a certain length of time. And it seems because you're underneath, we're talking about underground. So for underground areas like infiltration basins and things like that, they'll be pretty humid most of the time. And so I think the biofilm would survive pretty well.
Any other thoughts on that? Well, we are quickly running out of time for today's session. As I said before, I will take all of the questions that we received. I'll share them with our presenters so that they can have a chance to respond to your questions. That will go into a PDF that will get shared with all the registrants. So thank you so much for posting your questions. I'm going to actually move us into our kind of closing piece. Before I do that, I do want to thank all of our speakers, all of our presenters today for providing the information. We got a lot of really good information today. Obviously, with the number of questions that we had posted, I'm going to post some links in the chat and mention a few things before we close, as well as share my screen for just a couple short slides. So first of all, I hope you do tune into some of our future Stormwater Seminar Series events. In February, we'll be talking about road salt, impacts to not only stormwater, but surface water, groundwater, and ecosystems, as well as drinking water supplies. We have our national expert coming in to speak on that on February 23rd. I encourage you to join us if you're interested in road salt. But also I'll mention in April, we are currently tentatively planning to talk about media and engineered media and amendments that we put in often our rain gardens, our biofilters, our filtration devices. So kind of expanding on a bit of the topic we started today with what are those media, what do they do for us in terms of pollutant removal, and what can they possibly have for consequences or downsides, or how do they affect the performance of other aspects of our practices. So that's tentatively scheduled for April. When more details are available for that, we'll be sure and share that with you. Before I close, I do want to reiterate this Minnesota Stormwater Seminar Series is funded through the Clean Water Land and Legacy Amendment and the Minnesota Stormwater Research Council as an outreach arm of work that's being done here in Minnesota. So we're very thankful for the funding to be able to do these seminars. I'm very thankful for our speakers and panelists for being able to provide the content and expertise. If you are interested in looking at future seminars, we have links here for the full schedule, which again, I just posted in the chat. We also have recordings of, it will be soon, this event, as well as all past events are on our YouTube channel. There's a QR code there if you want to go there and check it out. Otherwise, the link again is in the chat. If you want to hear about next events that are coming up, including the road salt event or our media event or other events, please sign up for Updates newsletter on our website. And before we close, if you're interested in professional development hours, again, there's a link in the chat for that. Please fill that out. And we obviously very much value your opinion on our seminars and ways that we can improve and other topics or speakers that we could invite or cover in the seminar series. So there's a link for that also in the chat. Please go to those links. I look forward to seeing you at a future Minnesota Stormwater Seminar Series event. Again, my name is Andy Erickson. It has been my pleasure to host the Q&A. So thank you for your time. Enjoy the rest of your day. And I look forward to seeing you at a future event. Bye for now.